Now we're moving into our first four gas laws. And for the first four gas laws, we're going to focus on these three variables: pressure, volume, temperature. The last one we're going to focus on is the mole, but at this point in time, we're not dealing with the mole right yet. We're going to get to that with the ideal gas law. So as we go through these ones, we're going to focus on two of the three. We're going to keep one of them constant. So our first situation, we're going to keep temperature constant. So we're going to look at pressure and volume. So in this, we're going to reduce our volume. If we reduce our volume, we'll see that we're going to increase collisions. If we increase collisions, we're going to increase pressure. And this is where my pressure and volume are inversely related. And this is Boyle's law. Now, P times V equals K. So if my P is 20 and V is if my K, we'll say for example my K is 40. So if my P is 20, my V would have to be 2, so 20 times 2 is 40. If my P were to decrease down to 8, my V must increase up to 5, so 8 times 5 is 40. So they're always have that inverse relationship with each other. So the equation is P1 times V1 equals P2 times V2. And if we plot it out, it forms a hyperbola. Remember this hyperbola. This will be plotting this out in a graph in our graphing lab. So if I give you the values here, you would see right away that your pressure is actually increased by 2. It actually is doubled. Therefore, I know if my pressure has increased by 2, my volume must decrease by 2 because they have an inverse relationship to each other. If I did plug it into the equation and solve for my V2, I would get the answer of 5, which is expected, half of my 10. So that's Boyle's law. Boyle's law is P1 times V1 equals P2 times V2, and pressure and volume have an inverse relationship. Went through some examples there. Then we got the next one. We then focused on temperature and pressure, and we kept now volume constant. And this is an example of actually working with, dealing with Gay-Lussacs law. And so our argument here is we're going to increase temperature. If we increase temperature, we're going to increase kinetic energy. If we increase kinetic energy, that means we're moving faster. We're going to have more collisions. If we have more collisions, we're going to have an increase in pressure. So temperature and pressure in this situation, have a direct relationship, and this is called Gay-Lussacs law. And as we plot out in the graph, it gives us a straight line, meaning a direct relationship. So this one is P1 over T1 equals P1 over T1 equals P2 over T2. Know that equation. Also, really quick, we know that P divided by T equals K, so they're going to increase and decrease together proportionally, and so that their answer will always be equal to the same value K, which is a constant. The third law, I'm sorry, going back to this, we did some problems here. Now, one thing I do want to emphasize right here, right now with pressure and volume just remain consistent. As for temperature, temperature always has to be in Kelvin. So in situation 27 and 327 are both whole numbers, so I'm just going to add simply 273. And I realized my initial temperature was actually 300 Kelvin, final temperature was 600 Kelvin. So I realized that my temperature doubled. Well, since temperature and pressure have a direct relationship, and my temperature doubled, so must my pressure. So if we actually solve this one out, I started with 100 millimeters mercury, I end up with 200. My third equation, and now we're going to keep pressure constant and focus on temperature and volume. Our argument goes this way: that we increase temperature, we increase kinetic energy, increase collisions, but we're going to increase volume this time. So temperature and volume also have a direct relationship, and this is Charles' law. So V over T equals K. The direct relationship also plots out a straight line. So as V1 over T1 equals V2 over T2. In this situation, if I actually plug my information in, I have my volumes and I have my temperature, so I convert my temperature to Kelvin, and I realize that my temperatures have actually doubled. Then I know that my volume must also have doubled in this situation. So if my volume was originally 10, now it's going to be 20. So if I solve this out and actually solve it all the way through and solve, my final volume ends up with 20 as expected. So then we brought all three of these gas laws together and we combined them to form what we call a combined gas law. And so we see with the combined gas law, we have P1 times V1 divided by T1 equals P2 times V2 divided by T2. And so now all three of our variables are actually active.